Hello everyone and welcome back to another lecture. We're going to continue Unit 7 looking at Chapter 14, Pulsed Echo Instrumentation. Now if you remember back to when we talked about what ultrasound is, we talked about that it was pulsed echoes. We need to be able to send these pulses out, wait for them to come back, send those echoes, and then the machine gets those echoes, processes them, displays them, and then we can archive them or do whatever we need to do with them after that. And so we need to have instrumentation, our ultrasound machine, that can handle these functions. So we're going to start learning a little bit about the ultrasound machine guts itself. It's a little bit more conceptual again. It's not like pulling apart the body and being like, here's a spleen, here's a pancreas. We're going to talk about the parts. We don't necessarily look at them in the setting of the machine. We can kind of draw them out to kind of give you a relationship of them, but other than that, this is again pretty conceptual for how the machine operates. And this is a very basic machine. I just want to underline that. Very, very basic machine. This is not the machines that we are using now, but the same concepts are in practice. So the pulsed echo instrument, or our ultrasound machine, really has tons of features, but it's ultimately responsible for two things. The first one is the preparation and transmission of an ultrasound beam, and then to get it back, the reception. That is all it needs to do. It needs to send a pulse out. It needs to get that pulse back and do something with it. So that is what a pulsed echo instrument needs to do. There are going to be typically 6 components that create the ultrasound system. So of course we have our transducer. We have the pulsar and the beamformer. We have the receiver, the display, storage, and master synchronizer. Now in this lecture we're going to cover the pulsar and the beamformer and the receiver. We've already talked about the transducer quite a bit in depth, and our next unit will cover the display and storage. And then, we actually also talked about the master synchronizer in this lecture, but it's such a small part of it, I completely forgot. But as we are going through each of these anatomy pieces of the ultrasound system, if there are any other synonyms for what it does, make sure you know those synonyms. And as we get through the receiver part, and I guess part of the pulsar part, know if there's anything that you can do as a sonographer to change how the machine interacts with the sound beam. And so I don't have a picture of this in your notes. I should draw something and post it. But we talked about those 6 components, and I talked about, we're not going to open up a machine and take a look at each one, but basically what happens is we have the pulsar, and the pulsar is going to be getting the energy from the outlet, right? So the plug's coming in and into the pulsar. So the pulsar is ultimately responsible for the voltages that come out of the machine. So creates a voltage, and that's going to go down to our beamformer. And the beamformer is only necessary in pulsed echo machines. It's not necessary in continuous wave machines, but so beamformers have to be in our pulsed echo machines, because their beamformer is going to be the thing that creates all those patterns to steer the beams around. So the beamformer is going to get the voltage, and it's going to decide the pattern that goes out to our transducer. The transducer then is going to send sound into the body, and then it's going to get some sound back. The transducer then is going to send a voltage back to the beamformer, and the beamformer is going to do a little bit of processing, but for the most part it's all going to go over to the receiver. And the receiver has 5 functions that it is going to go through. After those 5 functions occur, it is then going to head off to memory, and this is what we'll talk about in the next unit. So the memory takes it and figures out how to put it on to our display. So we get our picture. The display then is available for us to visualize, but then we also need to typically store the ultrasound information that we get. So we're going to send from the display, we are either going to send it off to our PACS system, which will hold electronic images, or we can print them out on a piece of paper, or we can put them onto CDs, multiple different storage units in there. So again, power comes in from the wall through the pulsar. That's going to go to the beamformer. Beamformer makes the patterns, sends it to the transducer. Transducer gets that information back from the body, sends the information off to the receiver. 5 functions of the receiver, which we'll go over, and then we go into memory, display, and into storage. Now the one structure that I didn't talk about was the master synchronizer. The master synchronizer hangs out over here, and the master synchronizer listens for when these sounds come back and say, yep, we got all the echoes, you're good to go, pulsar, go for it. And the pulsar will send another voltage out. And then the master synchronizer is going to wait, make sure that all these pulses come back, and tell the pulsar again that it's good to go. So the master synchronizer kind of controls the actions of the pulsar and the beamformer. Right? So that's kind of the basic setup of your ultrasound machine and the order that things will work through. So let's take a closer look at some of these structures or components and learn a little bit more about them. So let's first talk about the pulsar. The pulsar is on during transmission, and the pulsar is going to receive the electrical energy from the wall. It's going to take that electrical energy and it's going to send out the electrical voltage that will excite the PZT crystals. So the pulsar has all the power, sends power out. The strength of that voltage that comes from the pulsar is going to determine the strength that the PZT crystals ring at. So we know that the power from the pulsar does have something to do with the strength. The way that the transducer is made is going to be how the frequency is created and all of that. So the strength of the sound beam coming out of the transducer is solely based on the pulsar. So stronger voltages from the pulsar are going to make stronger ringing coming out of the transducer, which results in strong reflections. And we know anything that has a strong reflection is going to be very bright. So typically with stronger pulsar voltages, we're going to have brighter images. The power that is put out by the pulsar has quite a few different names. And so the energy that's coming out of the pulsar is also known as output gain, the acoustic power, the pulsar power, energy output, transmitter output, just power, or just gain. Now I want to point out that using the term gain to refer to the pulsar voltage is not very appropriate. It can actually get very confusing. So typically, I would say the most common one is to refer to this as power. What is the power coming out of the pulsar? Now the power that comes out of the pulsar, the ultrasound energy that comes out of the pulsar, affects how the sound interacts with the biological tissue. And so there's a couple things that we pay attention to when we know that sound is interacting with biological tissue. And that's the thermal index, is how much power is in that beam to heat up the biological tissue. And then we also have the mechanical index. The mechanical index tells us, is the power, the ultrasound energy, is there enough power behind it to cause cavitation, which are little bubbles, and those little bubbles then can destroy cells. So we watch the ultrasound energy that is coming out of the machine, out of the pulsar, by observing the thermal and mechanic indices. And those are typically displayed on your image. The higher the number, the higher the power that is coming out. We'll talk more about this when we talk about bioeffects, but I just wanted to point this out now. You'll see this number change depending on what you're scanning. If you're scanning like heart or abdomen, you need a little bit more power to get more penetration. Therefore, our indices are usually a little bit higher, as opposed to if we were scanning a fetus. We would want to lessen our power to reduce those indices so we're not putting as much ultrasound energy into the body. So if you look at the different settings on your machine, flip through some different settings, and then pay attention to what happens with your thermal and mechanical indices. Another thing that's very important about the pulsar is that the output is adjustable by the sonographer. So on your machine, there is, okay, I'm going to back up a little bit. Older machines typically had a very obvious button that said power, and it's not the on button for the machine, it actually said power, and this referred to power of the pulsar, the power output that the pulsar did. Newer systems now, if you can even change the power at all, again, they hide this into submenus, mostly just because this really affects bioeffects. If you really crank that power up, you're increasing your risk for bioeffects for your patient. So typically they don't give as much freedom to change the power of the system in the newer systems. Anyway though, there are some that still have it. You can still get in to adjust it. Another way that you can adjust the power as well is to select the appropriate preset. Again, if we were scanning something like the abdomen, something that needed penetration, the machine knows that you need more power and therefore will increase your power for you compared to like a fetal heart or scanning a first trimester fetus. Another thing that occurs when we are ultrasounding is the idea of noise. And it's probably something that you haven't thought a whole lot about, but when the machine is sending in these ultrasound energies into the body, there is going to be some reflections that just kind of bounce off of everything, and it's all just kind of coming back to the transducer. And some of it's meaningful, and that's where we get our outlines of our organs, and that's all fine and dandy, but some of it's not meaningful. And that not meaningful ultrasound energy that's coming back is just noise. And because of it, then we kind of get this low speckling across our pictures. You know how everybody just says like, oh, everything just looks like grainy, it's grainy gray blobs on there. That's kind of the noise coming back. We've gotten very accustomed to being able to see borders and picking out structures that noise is not as apparent to us, but it is still something that is in our image. It kind of just muddles the picture a little bit more. And so we can think of the signal to noise ratio as an important concept of us being able to see the structures better in the body. So the signal to noise ratio compares what are the true echoes coming back from important structures within the body versus the noise or just like kind of the contamination that's in our image. When we have low signal to noise ratio, that means we have a weak signal but consistent noise. That noise is always there, but we have a weak signal going along with it. And because of that, we're going to get a low quality image. I really like this picture because it kind of shows, we can still read that this is signal. You'll still be able to tell that you're looking at a liver or the mitral valve, but it's going to be kind of faded into the rest of the picture. This is a low quality picture. Compare that to high signal or a high signal to noise ratio. We get a really strong signal. That's going to be really crisp borders on our organs, really bright echoes returning from the diaphragm. Strong signals, still with that consistent noise. The noise didn't change. The signal just got way stronger. And when we have a very strong signal, we get high quality. Well, to get that strong signal, we need strong ringing. And that's why this is in this section, because it all comes back to the power that is being put out by the pulsar. If we increase the power that is coming out of the pulsar, we increase our ringing, or the signal that we're putting in, which then increases the signal to noise ratio. So we get better images when we have more power coming out of the machine. The problem is though, is that we don't always want that strong power. Again, going back to bioeffects. Are we putting too much ultrasound into the body? So remember that increasing the output power will increase your signal to noise ratio, A high signal to noise ratio improves the quality of your picture. PRP pops up in this section as well because we're kind of getting into the timing of everything. So remember, the pulsar is responsible for sending out the voltage that the beamformer will then make into a pattern and send to the transducer. But the pulsar can't go until all of those echoes have returned. And that's what the master synchronizer's job is to do. It is going to listen for those echoes coming back from the maximum depth, and once it thinks all those echoes are back from that depth, then it's going to tell the pulsar to go ahead and send its next voltage. And so PRP pops in here again because the more depth you have, the longer the PRP, which means more time in between the pulsar transmitting new pulses. So that segues us into master synchronizer then. Again, the master synchronizer is listening and timing all of the machine controls. So it's telling the pulsar to go. Pulsar sends out its message, its voltage. The master synchronizer waits, knowing what the maximum depth is set up, waits for all those echoes to come back, says, okay, pulsar, we've got them all, go again. And so that's kind of what the master synchronizer is doing. It's paying attention to the range or the depth that the machine is set at, and then controls the pulsar for its timing. So after the pulse or the voltage leaves the pulsar, it's going to head to the beamformer next. A beamformer, again, is only found with our array transducers. So remember, array transducers are multiple transducers or multiple crystal transducers. So if you need a pattern or you need that beam split up into a certain way to either steer it or to focus it, then you need a beamformer. The beamformer is going to take the pulse from the pulsar, and it's going to divide it into those channels, telling those crystals how to utilize the pulse from the pulsar. So again, beamformer only found with array transducers. You have to have a beamformer if you are using an array transducer. The other big part about the beamformer, not only is it operating in transmission when it's sending those pulses down the channel. Remember, we have receive, focus, and dynamic aperture in reception. That's also going to be on the beamformer. So the beamformer operates both in transmission and reception. So while it is operating during transmission, again, the beamformer is going to receive one big voltage from the pulsar. And then the beamformer needs to figure out how to distribute that voltage down the channels. Remember, the channel is the components in the beamformer, the wire, and the PZT crystal. So the beamformer decides, this is the pattern that we're doing for this pulse. It's also going to change which crystals are being used, so that's that dynamic aperture in transmission. It's going to create that complex pulse to steer and focus. And remember, apodization reduces our grading lobes, and so it's going to include apodization within its complex pattern. So the beamformer is responsible for the focus and steering of each scan line that is created. So that's all, it's doing all that during transmission. During reception then, the beamformer is going to establish what crystals are going to be used during reception, so that's that dynamic aperture in reception. It's also going to determine then how the voltages are going to come back into the machine. So it's going to correctly delay the voltages coming back, and that's that dynamic receive focus. So that's the beamformer's job during reception, is to use the right aperture and then focus the voltages coming back. Modern systems use digital formatting of the beamformer. So before, it was this kind of analog processor. It had moving parts into it, and whenever you have moving parts, things break. It's just not as stable. And so our modern systems use digital beamformers that are basically little computers. So that's the microprocessor. They're little computers that figure out how to distribute the voltages. And the awesome part about having the digital system in there now is that you can upgrade your beamformer just with uploading different software. They're very stable. There aren't any mechanical pieces in there, so they don't need to be calibrated or are worrisome for breaking down. And the other really awesome part is that they're versatile. They are capable of operating many transducers at many different frequencies. So any one unit, any one modern unit now can have up to like 21 transducers that it can operate with. That was not the case for the older systems. You maybe had one transducer that had one beamformer that it could operate with. And so updating to the modern systems gives us so much more functionality to our systems. This wasn't on our list, but the switch is a very important little piece of equipment that sits within the beamformer area. And basically what the switch is doing is telling the machine, are we transmitting right now or are we receiving right now? And so the switch, when we're in transmit mode, kind of protects the receiver from any damage that the pulsar might cause. The pulsar is sending out a really strong voltage, and the receiver is used to getting really tiny weak voltages from the echoes that are returning from the transducer. And so when it is in transmit mode, the switch turns to transmit and protects the receiver from these really strong voltages. When everything is switching over into receive mode, the switch then switches also to receive, and that's going to then allow the weak echoes returning from the body, those weak voltages then going to the receiver in the appropriate way. So the switch is basically the receiver's protector so that it doesn't get fried by the really strong voltages coming out of the pulsar. So speaking of the receiver, we have the receiver is going to be the next component that's going to receive the echoes. So I just kind of want to recap what we talked about on the whiteboard here before we get into the receiver, because this is its own beast on its own. So remember, we have our outlet, comes into the machine and into the pulsar. Pulsar is going to get the okay from the master synchronizer, say it's okay, sends its pulse out. Pulse, that big voltage then gets to the beamformer, and the beamformer is like, okay, this is the pattern we're doing, send those down the channel to the transducer. Transducer then sends out the sound energy, and then it's going to get echoes back. And remember, those echoes coming back are very weak. Oh, and I should say in here too, as all of this is on, the switch is up to transmit. Okay, so now we've transmitted, echoes are coming back, the switch moves down to we're in receive mode. Our echoes are coming back. Remember, they're really weak voltages. The beamformer does a little bit of processing for them, but it mostly all gets sent over to the receiver. Okay, so now we're in receive, we're heading over to the receiver, and we are going to process through 5 different functions of the receiver those really weak voltages that came back. And the whole job of the receiver is basically to process those voltages and get them ready to be displayed on a monitor. So there are 5 functions that the receiver is going to do. They do them in this order, and you will need to know this order. Notice that they go in alphabetical order. So after you memorize what the 5 functions are, to remember the order, just put them in alphabetical order. So we're going to go over each of these a little bit more in detail, but all the voltages coming back from the echoes out of the body are going to go through amplification, compensation, compression, demodulation, and rejection. So again, as we're going through these, pay attention to alternative names and if you can adjust it as the sonographer. So our first process in the receiver is going to be amplification. Amplification is required because those signals, those voltages that are coming back, are super weak. And so all signals must be amplified or made bigger so the machine can use them and manipulate them. So amplification is known as receiver gain. And the receiver gain is displayed on your image. Typically you'll see it in a decibel form somewhere off to the side. Sometimes you'll see it as a percentage as well. But receiver gain, when we increase the receiver gain, we take all the echoes and we make them brighter. There's no discernment between which echoes should stay dark. Nope, they all get the same amplification. So no matter how you change the amplification, you can increase or decrease the gain, all the signals undergo equal amplification. It is important to note that amplification does not improve the signal to noise ratio. That's because it's going to also amplify the noise. So it amplifies the signal and the noise. And amplification also does not uniformly make a picture bright. If you already have a dark near field and a bright far field, your far field is just going to get brighter along with your near field getting brighter. So amplification treats all the signals the same. Amplification is adjustable. Typically it's labeled on our machine as gain. I'm sure you've used it quite a few times already at this point, but that is the knob that tells the receiver to amplify the signals that are coming back from the body. Our typical values for amplification then range in between 60 to 100 decibels. And again, remember that amplification is measured in decibels. So it's a change, a ratio of numbers. What you will see with a lot of the functions of the receiver is that there's kind of like a first function and then there's a second function. The first function is usually not controlled by the sonographer. So same idea with amplification. We have pre-amplification, which is an automatic thing that the machine does. It's getting those really weak signals back from the body. It's going to amplify them no matter what. We just need bigger signals to work with. So the machine's going to amplify them no matter what. And then you as the sonographer can amplify further if you want to create a brighter or a darker image. The second function of the receiver then is compensation. Compensation is going to allow the machine to assign similar echogenicities to similar structures. To say it in another way, compensation allows us to compensate or to make up for attenuation. So if you think about when you're imaging, and we know that sound gets weaker as it moves into the body, that makes our near field usually a little bit brighter than what our dark field is. So we need to compensate for that attenuation and make the far field a little bit brighter. So if we didn't have compensation, our pictures would look very dark in the far field and very bright in the near field where the signal is strongest. With compensation, we can create uniformly bright from top to bottom pictures. So here is an example of an uncompensated view of the heart. Our signal is very strong up here. Remember, strong signals have brighter reflectors. And we know that the sound is attenuating as it propagates through the soft tissue to where we get that darker far field. When we compensate for attenuation, we now can create a picture that is even all the way through. This is much more pleasing to look at for the radiologist. This will also indicate then, say there's a large tumor or myxoma in the heart, that would show up in here because it is not being, it's made of different tissue than what we have assigned to the rest of the tissue. So having a correctly compensated image also helps pathology to stand out better. Compensation is adjustable by the sonographer. Now, modern systems, again, are going to do kind of its own compensation, knowing that the machine, or knowing that sound attenuates as it moves through the body. There is going to be some compensation done by the machine, but you, as a sonographer, also can control the compensation that occurs. So compensation is also known as time gain compensation. Those are your TGCs. Sometimes they're referred to as DGCs for depth gain compensation, and it's also known as swept gain. So again, another area that you've probably have manipulated in your pictures, not knowing quite what you were doing with it, you've been compensating for the attenuation that occurs in your image. So we usually have these little sliders somewhere on the board of our ultrasound machine, and what these sliders do are compensate for the attenuation that's occurring, or the lack of attenuation even. So the top sliders are for the near field of the machine, where the bottom sliders are going to be more for the far field of the image. As you move the sliders to the left, typically are going to get darker. If you move them to the right, the area typically gets brighter. So again, most of our modern systems are going to compensate automatically for the fact that there's attenuation, and then we use our TGCs to kind of do really fine-tune manipulation of our picture. Older machines, you had to set the compensation for the machine, and so every machine had some sort of angle of the TGC knobs to create that compensation. Compensation is also measured in decibels, again comparing the ratios of the numbers coming back. So why do we compensate? Well, again, because of that attenuation, but furthermore, I just told you that modern machines are going to do a lot of that compensation for you. You get to go in as a sonographer and kind of get that artistic eye to creating a better picture. We know that we want structures that should be anechoic to be anechoic, and sometimes we just need to adjust our TGCs to get that. And so we can use our gain to reduce the overall brightness of the echoes, and then we can use our TGCs to ever so slightly alter the echoes that are coming back just to make the picture uniform. So again, another example, we have an image of a liver here. Our image in the near field looks very nice. We can see all the structures, but now we've attenuated in the far field and can no longer see the liver structures. So what we need to do then is slide our TGC knobs to the right to make that far field brighter, and then we will assign the correct echo brightness to that far field to make the picture appear uniform. So TGCs are going to help us to create uniformly bright images. As you move the TGCs around, some of the displays will show you your TGC curve. This is an example of it here. It kind of shows us that we don't have as much attenuation or as much compensation occurring here, and then we are compensating, making the image darker in the far field. And we can see that in our picture as well. Very bright in the near field, dark in the far field. So again, the TGCs usually on our modern systems are going to be used to create an ever so slight curve just to kind of help fine tune the image. I never want you guys to take one knob and just crank it all the way to one side or the other. That is not how we clear things out. You need to use more pressure, you need to use your gain, you need to set your TGC curve to a nice slope. You should never have these like jutting in all different directions. They're almost always should be in a nice slope if they're not straight up and down through the middle. As I mentioned before as well, older machines you had to set a TGC curve because the machine did not automatically compensate for you. So we would bring our TGC knobs more towards the left, make them darker in the near gain because that's where the signal was strongest. We would then have a gentle slope moving down to the far field, making the far field brighter and increasing that far gain. So there are names for each of these sections. You should know them for your boards. So remember again the knobs on the top, adjust the near gain. When we start to create our slope is where we have the delay. We then have the slope is the angling of the knobs as they move down towards the knee. And then the knee is the beginning of the maximum gain in the far field. So I just want to go back to another picture here. Again, we have the near gain, the delay, the slope, the knee, and the far gain. And again, all of our slopes are going to look different. Again, near gain, delay, slope, knee, far gain. So you can kind of see how there's similarities to the slopes. None of these are jutting out in any one direction. That's not part of our TGC curve. Right, the third thing that the receiver does then is compression. We actually have a whole chapter on compression, so we will talk about this, I believe, in the next unit. But it is part of the receiver, and just like the other ones, there's a first compression and a second compression. So the first compression that the machine does is required for the machine to keep the signals in a range that it can use. And we're going to learn again more about this in its dedicated chapter. But what happens is that the transducer sends back tons of information, like just so much information, and the machine can't really handle all of it. And so what the machine needs to do is say, all right, really strong echoes, we need to keep you strong. Really weak echoes, we're going to keep you weak, but we got to get rid of this extra information in between. We don't know what to do with all of this. And so the first compression is taking all that extra information and kind of getting rid of it so the machine can process what is left. So now the machine has what it can handle through the first compression, and that's where second compression comes in. And that is something that you can change as a sonographer. There is typically a knob somewhere on your machine called compression, or I believe there's some other names for it here. Pull that slide up. Compression or dynamic range is usually what it is labeled. And with that second compression, what you're basically doing is telling the machine, I know you've got the capability of 256 shades, but show me this picture using only 20 shades of gray. So when you compress the image, when you change things as a sonographer, change that compression, you are changing the amount of choices of grays that the machine has. So if you increase the compression, then you are asking the machine to use less amount of grays to make the same picture. So white still stay white, bright still stay bright, darks are still black, but now you're losing those grays in between. So let's look at this picture here. So here we have broad dynamic range. So that means there's lots of choices. This is low compression. So low compression, broad dynamic range. Lots of gray choices. When we increase the compression or narrow the dynamic range, we start to get a little bit more black and white. And so this is the exact same picture. We can still see, we have air here. This is still bright white in both pictures. The capsule around the liver is still bright white in both pictures. Vessels are still pretty dark like they should be, but now they've just kind of crispened up a little bit. Those extra grays are gone. We have reduced the choices of grays to be displayed. The biggest thing with compression, again, we'll talk about it later, but the biggest thing with compression is that your strongest signals still stay strongest, your weakest signals are still weakest. The fourth step the receiver goes through then is demodulation. And this is the first one that you cannot change. Demodulation occurs automatically in the receiver. So when the machine gets those echoes back from the transducer, the echoes that are returning have above and below the baseline. If you think back to all the pictures we've been drawing showing echoes or showing how pulses go out, we typically draw something along the lines of this, right? We have above and below the baseline. Well, the machine doesn't know what to do with the below part. Can't figure it out. So that's where demodulation comes in. With the modulation, 2 steps must occur. The first one is rectification. So basically, rectification takes anything that's below the baseline and just flips it above the baseline. So now you get kind of these weird lumps all on one side of the baseline. So that is rectification, flipping negatives into positives. The next thing that occurs during demodulation is smoothing or enveloping. And it kind of takes the average of what's happening with those pulses and just makes it one line of information. So say our pulse is coming in. That's not a very good drawing. Let's try that again. Let's say our pulse comes in and let's say this is 30 and 20, 10, 5, 3. And then rectification happens. And so then we get something like this. And we still have 30, 10, or 30, 20, 10, 5, and 3. Well then, demodulation will come in and say, all right, well, we've kind of taken all these values that are represented in this pulse, and we're just going to average it out. So if we add these together, we get, what do we get, 50, 65, 68. Well, now we're just going to say we've got 32. And that's the information then that gets sent on to the display. The display needs kind of less options, even more so, to work with to be able to process these. So this information is going to head off to the memory for processing, so the machine knows how bright of a number or how bright of a pixel to display. And again, we're going to talk about more of this in the next unit. But for this unit, remember, demodulation occurs with rectification first, flipping negatives into positives, and then smoothing or enveloping, where we kind of get an averaging of all the energy information within that pulse. The machine components can handle that simplification or simplified information much easier, and so that is why demodulation must occur. Demodulation is also known as detection, so remember that. And again, demodulation cannot be adjusted. It is automatically done by the machine. It has to occur. The last thing that we have in the receiver function then is rejection. And rejection is the machine taking a look at those signals that it received and saying, nah, that one's too weak, let's get rid of it. It probably doesn't give us all that much information. And so rejection is getting rid of low level echoes. There is, again, 2 rejections, first and second rejection. First rejection is going to happen automatically. Again, the machine can't handle all the information coming back from the transducer, so it's going to automatically choose to ignore really low level echoes. As a sonographer, you have the option to increase the rejection or change the threshold or suppression. So 2 names for rejection, threshold or suppression. And you can tell the machine, all those little low-level grays, I don't want them anymore, get rid of them, make them the same as anechoic. So here we have an image. We've got lots of kind of speckling going on, lots of grays, and we're slowly decreasing or increasing, I guess, the rejection, saying get rid of those low-level echoes, I don't want them. And so in the final result, we get a very nice cleared out vessel here. And so we can still see the vessel walls, we still see structures, we can see the lineation through the soft tissue, but now we've just gotten rid of those low level echoes. So we'll go back to the whiteboard here. So remember, demodulation occurred, and Let's say we had some really big echoes, we had a tiny one, kind of a medium one, maybe this one. And so the machine already went through and got rid of all the tiny ones. As a sonographer, maybe our rejection is set here. And so now this little information here, no longer even going to be displayed. The machine, you are rejecting it. You don't want that information. Let's say you've on your machine then turn the knob up and you increase your rejection to maybe here. Well, now this one is no longer going to be displayed either. So now we're only getting echoes that surpass the threshold that you have set. So again, rejection gets rid of those low-level echoes that can kind of contaminate or make our picture look more grainy than we need. So those are the 5 functions of the receiver. It is important that you remember the order that they go in, what each one does, if it has any other names, and if you can adjust it as a sonographer. I also really strongly suggest that you guys go back to your machines, and while you're scanning in Open Lab or during class time, take a look at those things that we talked about that you can adjust and see what happens when you adjust them. Pay really close attention to it. The more you can practice physics, the better you'll understand it and then be able to relay that on to a written test. All right, so we're going to kind of go off into a couple tangents. We've discussed those components that we talked about. The rest of the components we'll talk about in another unit. But before we leave this area, we need to talk about dynamic frequency tuning. So dynamic frequency tuning reinforces the idea that we want short pulses for better axial resolution. And so if you recall, short pulses improve our axial resolution. Short pulses are typically created in probes with backing material. And when you have backing material, your short pulses are going to have a greater range of frequencies or bandwidth. So what dynamic frequency tuning does then, it utilizes those bandwidths to optimize our image. So dynamic frequency tuning is going to use higher frequencies within the bandwidth to process the near field echoes. It's going to then use the middle frequencies to process the middle portion echoes, and then it uses lower frequencies for the far field. This all kind of comes back to the beamformer and the receiver working together to process the picture in the correct way. So again, if we have our image here and our pulse is sent out and we kind of have something like that, we're going to use our high frequencies for this first section here. We'll use our middle frequencies to get information from the middle section, and then we'll use our lower frequencies for the far field. The beamformer is responsible for kind of understanding how these frequencies are coming back and listening for it. Again, way beyond the scope of what you need to know, but know that dynamic frequency tuning utilizes the different frequencies emitted by the transducer to process different levels of the picture. And the beamformer and receiver both play a role in how those echoes are processed. All right, I think we're on just about to our last concept here. So we talked earlier about how the pulsar is responsible for putting out this giant voltage, and the stronger that voltage is, the stronger the echoes from the transducer are going to be. It's going to ring stronger. That means more ultrasound energy gets put into the body. And then we talked about the more ultrasound energy that gets put into the body, the more concern we have for bioeffects. And so with that thought in mind, we have something that we need to adhere to as sonographers to use the Olara Principle. Now, Olara stands for as low as reasonably achievable. So that means, what is the lowest amount of power that you can use and still get a good picture? We don't want to max our power out for every single image, sending these really strong ultrasound energies into the body. We don't want to do that. We can amplify things by using receiver gain. We can increase the brightness using our TGCs. There are other tools we have other than just cranking the power and going for it. So Olara says, use as low as reasonably achievable. A big part that you're going to play in this is to select the appropriate presets, to be aware if you can change the power on your machine, are you changing it appropriately before other parameters, and to reduce the amount of time that a person is exposed to ultrasound energy. So the Olara Principle, again, reminds us that we want to use as little power as possible to still create a nice image. By understanding what output power can do to an image versus the receiver gain is very important, and this chart shows this nicely. So output power is going to change the entire brightness of the image. The brighter or the stronger those echoes are going out, the stronger everything will ring, the stronger the echoes are coming back. So the brightness does change when you change the power. The output power alters our signal to noise ratio. So if we want those really crisp borders, we need to use a little bit of power behind our echoes. But it also then alters the patient exposure. So the stronger the power is from the pulsar, the more concern we have for bioeffects. So knowing all of that, if our image is too bright, then we should decrease output power first. If our image is way too bright, then there's no reason to have that much power going into the body. So we should decrease the output power first. Now when we switch over and look at the receiver gain, we know that it also changes the entire brightness of the image, but it doesn't have an effect on that signal to noise ratio. So if we can see everything well enough, then receiver gain should be all we need. When we change that receiver gain around, it has nothing to do with patient exposure or bioeffects. It's all in the machine, how the machine is processing those echoes. So if our machine is producing a picture that is too dark, then the first thing we should be doing is increasing our receiver gain. So again, just to kind of walk through the process and the thought process with this with Olara. You're scanning a patient, your picture is super duper bright. The first thing you want to do is turn down your power. Bring that power down to a point where you still have a good image and can see everything appropriately. You're good to go. You're using the appropriate amount of energy. Contrary to that, you're scanning a patient and the image is too dark. The first thing you want to do is increase your receiver gain. We want to see, can we just up the gain and not put the patient at risk for more ultrasound energy? If you max out your receiver gain and everything is still too dark, then absolutely, you can increase your power to further brighten the image. Lastly too, don't forget about your TGCs. If you need to make things uniform, neither output power or receiver gain are going to do that. TGCs are safe. They're not going to change the bioeffects concerns. So keep that in mind as well, that you may just need to bump some TGCs around to get the appropriate picture. So for Olara, make sure that you know what Olara stands for. Know the concept of when you should decrease power versus increasing receiver gain. As far as the rest of the stuff, know the 5 functions of the receiver, the order that they go in, synonyms, if you can adjust it. Understand the signal to noise ratio concept and understand what each component does, if they're working during transmission or reception, and the order that they go in.